Good afternoon, everyone. My name is Niladri Gomes, and I'm going to talk about an adaptive variational approach for quantum simulations. This work was done in collaboration with my former colleagues at Ames Lab. So, here is the plan of my talk. I'm going to first motivate the kind of problems that we intend to solve in the long run using a quantum computer. Then I'm going to introduce certain fundamental concepts in quantum computing. Then I will introduce the idea of variational quantum algorithms. And then on the top of it, I will discuss the time dependent approach and discuss its limitations. And then I will introduce our adaptive approach and show how we can use it to solve the limitations of the fixed variational algorithm. And then I will use our method to find solutions to certain quantum chemistry problems, and then I will conclude. So, why do we need the quantum computers at all? It turns out that there are certain real life problems, for example, problems in quantum chemistry and in condensed matter physics, that are completely intractable using classical computers or the conventional computers that we have. Let's say take the example of how the enzyme nitrogenase captures nitrogen from the atmosphere and converts it into ammonia. That is a big mystery even today. It is believed that in the enzyme there are certain active sites which contain molybdenum and iron, which are electron-rich elements, and the electrons they interact with each other. Such interacting electronic systems, they have many degrees of freedom, and storing information about them using the classical computers, it's extremely hard and it is almost impossible to simulate such systems. Another example are the high temperature superconductors. Uh, if we dope copper oxides, they start superconducting below a certain temperature. Now, in case of superconductors, we know that the resistance is zero, which means there is a lot of energy savings while we send the current because there is no heat dissipation. So all of these problems, they are kind of practically insolvable using the current state-of-the-art classical computers. So what is different in quantum computers? Starting from the classical computers that we have, there, if we want to store information about anything, we have to do that in terms of classical bits, and the classical bits, they exist in binary form. That is, the informations will be stored in terms of 0 and 1. Now, for those who know how the quantum states they scale, they will know that they scale exponentially, which means if we want to store the quantum states using the classical bits, we will soon run out of memory because we need exponential resources. Back in 1982, Feynman suggested that we switch to a different kind of bits. Those are the quantum bits or the qubits, using which we can store information about quantum states. I am showing a schematic example of how a quantum bit or a qubit might look like. So a quantum bit can, aside from taking values just 0 and 1, it can also take a linear superposition or linear combination of 0 and 1 states, which looks like this, where alpha and beta can be imaginary. So we can represent a qubit within a sphere like this, where any direction within this sphere centered here and pointing towards the edge, that will be a qubit. So immediately you can see that a classical bit, it's not binary anymore. It can take any value within this sphere, and that's why we can store much more information using a quantum bit compared to a classical bit. Clearly, if we use quantum bits to store information about quantum states, there is a huge saving in resources, because then the resource will grow polynomially. Now that we know a bit about what quantum bits are, what do we do with them? That's the next question. In the beginning of my talk, since I mentioned that as of now, we are mostly intending to solve problems in quantum chemistry and condensed matter physics, so invariably we would want to solve the Schrödinger equation, which is just a differential equation which looks like this. For those who are not familiar with quantum mechanics, please don't worry, because this bracket, the if we are looking bracket that encloses phi, it's just, for now let's assume that it's just a vector which can have complex entries, and this H is an operator. It can be represented as a Hermitian matrix. What we want to do is we want to solve this differential equation, and once solved, it typically looks like this equation, where we know how the solution phi looks like at tau equals 0. By the way, tau is time, and it is related to the solution at tau, at some non-zero tau, by this, where this U is a unitary matrix. Now, with all that information in our hand, we now want to build a quantum circuit. We want to represent this solution in terms of a quantum circuit. Here it is important to mention that a quantum circuit is quite different from what we learn in the traditional electricity and magnetism courses about circuits. This is not a traditional electrical circuit. Instead, a quantum circuit is a set of operations that we perform on a set of qubits. To understand more clearly, let's focus on this figure, where Q1, Q2, Q3 are some qubits, and let's say at time tau equals 0, these three qubits represents the quantum state phi. Now our goal is to decompose this U, the unitary matrix U, in terms of certain smaller operations that will be performed on the qubits, so that the entire thing will represent U. And after application of all of these operations, we will recover the state phi tau. And this, the span over which all of these operations are done, it's called the depth of the quantum circuit. Here I would like to mention that these quantum bits, or the qubits, they are operated at a very low temperature in the lab, and the temperature is of the order in the order of absolute 0, which means they are very hard to maintain. And at the same time, these operations on the qubits, they are equivalent to applying some laser pulses on the qubits in order to excite the qubits. So clearly these can be very unstable. These operations can make the entire systems very unstable. So while we decompose U into such multiple operations, our main goal would be that we minimize this number of operations. That means we want to minimize the depth of the circuit, because more the number of operations we use, these will bring in more noise in the final solution phi of tau. None of the computers that exist, they are purely quantum mechanical as of now. Since we already have very powerful classical or conventional computers, like the high-performing computers, what we want to do is we just want to extract the hard part of the problem and solve it in the classical computer, in the quantum computer, and then use that information, send it back to the classical computer, do some processing of the data, and if needed, we will send some feedback to the quantum computer, and that's how we will run it in a cycle until we reach some convergence. And since we are making use of both the classical and the quantum computer to solve a difficult problem, we call this a hybrid approach. All the approach that exist so far in the field of quantum computing, all of them are hybrid in nature. Now, there are many algorithms that exist nowadays to run on the quantum computers. However, because of tremendous noise in the current age quantum computers, the most widely used method is the variational method. In case of variational method, we'll try to approximate the solution phi in terms of certain variational parameters theta. So in this equation, psi of theta is kind of approximating or representing the state phi, and psi of theta is written in this functional form where thetas are the variational parameters, and psi of 0 is the state at tau equals 0. Now there is a reason why we choose this exponential form of the parameterization. This is precisely because such operators can be represented as operations on the quantum bits. In any case, using such a variational form, we now evaluate the cost function within a quantum computer. That's what I'm showing it in this green box. We send the data and optimize the cost function in a classical computer, just like the hybrid method I mentioned. When solving a time-dependent problem, if we choose the cost function wisely, we can arrive at an analytical form. With that, we arrive at a differential equation in terms of the variational parameters theta. So theta dot is the time derivative of the variational parameters. M is a matrix and V is a vector, and the elements of M and V can be computed or obtained from the quantum computer. We can now solve this differential equation in a classical computer to obtain an updated value of theta, and we will use this new theta to update our variational form, and we will run this in a cycle until we reach the desired solution. At this, we should be aware of two important points. The first being that it's very obvious from this form that more the number of parameters that we add into the variational form, greater will be the accuracy. But adding more parameters here, it means we have to add more operations on the quantum circuit that will increase the depth of the quantum circuit. So remember, increasing the depth of the quantum circuit means there will be more noise. So although increasing the number of parameters might bring in more accuracy, but it will also bring in more noise from the device, and that's why we have to create a balance between the two. We have to choose the parameters wisely in a very optimized way so that the noise is not much, as well as we reach the desired accuracy. It's crucial to remember that if we use a fixed number of parameters, the accuracy will be always limited. So is there a way out? Is there an optimized way of choosing the parameters or the number of parameters? Turns out, yes, we do, and that's where our solution comes in. In order to differentiate between our method and the method I described previously, I am using these two cartoons. The one on the left is the one where we can use a fixed number of parameters. That is something like we start from a reference state, and that's when a spider, let's say, falls from an altitude and it reaches the ground here, where the size of the spider, it doesn't change. The spider doesn't expand. It's a fixed size thing. And here is where our solution is. We make the solution, we make our variational form, which we call the ansatz, as flexible. And we compare this like flight of a parachute, meaning when we start from an initial reference state, and then where the number of parameters is minimal, or let's say 0, which is like the parachute, the size of the parachute is very small, but then it starts falling towards the ground, where it keeps expanding, but it doesn't expand indefinitely. Beyond certain point, it saturates, and our algorithm is smart enough to decide which parameters to add and when to saturate, by taking care of the fact that we don't lose the accuracy of the simulation. Before I apply our algorithm to certain real-life problems, I want to mention that our algorithm also has a byproduct. We call it as the quantum Lanczos method. Here, we run our time-dependent variational approach, we generating quantum states which are parameterized by certain number of variational parameters. Using only those states, we create a vector space which is much smaller than the entire vector space that spans over the particular problem that we are dealing with. Clearly, now if we try to solve the problem within that small subspace, it will be time efficient and memory efficient. And we have seen that in certain cases, solving the problem within this smaller subspace, what we call as the Krylov space, it might provide us faster convergence. At this point, it is important to emphasize that the method of quantum Lanczos, it is not an independent method. We need to run our algorithm in order to generate each of these quantum states, and we extract information from our adaptive method at each time step to generate the Krylov space. Here is a sample result. We applied our adaptive procedure to find the ground state of a molecule with 4 hydrogen atoms with 4 electrons. That's what the H4 is for. And the plot to the left is where in x-axis we have the time tau, and y-axis we are plotting the energy of the system. And if we want to reach the ground state of H4 molecule, and the exact energy, it is shown here in the blue dashed line, and the dotted blue line is where our adaptive approach comes in. That's the data. We see that we start from a high energy state, but then it smoothly converges to the desired ground state value. When it comes to quantum Lanczos, what we do is we select the states from each of these points as we run our adaptive algorithm, and using only those states, we keep updating. We keep solving the Hamiltonian using within that subspace, and you can see that the convergence can be much faster. To the right is the interesting plot of how the number of parameters change. Here x-axis is again time, and y-axis is the number of parameters, and theta. You can see that we start from 0 number of parameters, then our algorithm selects or chooses the operator smartly enough. That's how the number of operator increases, and finally it saturates. We have also applied this problem to multiple other cases of finite size molecules. Each of these represent the solutions for different kinds of molecules, and each of these colors, red, green and blue, they are representative of different bond distances. By bond distance, I mean the distance between 2 atoms within the molecule. In each of these plots, y-axis is the error, meaning the energy of the time-dependent quantum state, and we want to reach this exact energy. It's the difference. We can see that after a certain time, our algorithm is able to take us to the desired accuracy, which we call the chemical accuracy, which is below 1 kilocalorie per mole, which is below this gray region. So essentially our algorithm works well for these quantum chemistry problems. With that, I have come to the end of my talk. Clearly this work, there are many challenges. One biggest challenge is the amount of noise that the current devices have. We do need to do a proper and systematic study of how our algorithm behaves with respect to the noise in the real device. And of course, we want to apply this algorithm to study real-time dynamics in real materials where we see quantum dynamics. Thank you.